Okay, welcome everybody to today's ISTD seminar. I think analysis and story, it is. So it's our pleasure today to host, I must pronounce his name correctly, otherwise we get angry, Roberto Verbini. It's enough. He's responsible of an important lab here at ESRF, the Crystal Analyser Lab. And just a couple of words, we have been witnessing an explosion of inelastic X-ray and not only neutron beam line scattering beam lines. And it's important because this is good news for Roberto and his lab, because he's producing the crystal analyzers which are needed for these purposes. So we will see a series of spherically bent, but also cylindrically bent crystal analyzers. He told me that he has been working on such subject for 20 years, so expertise is not what is missing, right? It's lacking. And I want to say that the facility he will show is in its genre. It's unique in Europe in terms of the entire workflow of things he can do. So he will show the machinery and the miracles he can do and the production rate. And it's a good source of income, by the way, yes, as he will say. And there are a couple of things which I enjoyed listening yesterday. For instance, I didn't know that it is so difficult to move from Johann to the Johansson geometry of bent crystal. So he will show, he will unveil many details of what he's doing. And please, Roberto, the stage is yours.
So, good afternoon to everybody. So, my name is Roberto Verbini. I'm working in the optics group since 2 years now already. I'm actually responsible of the Crystal Analyser Lab and also the Crystal Analyser Laboratory. So, before I was working for many years as a benign operation manager on the ID20 and the ID28 beam lines. During all this year, I had the possibility to work quite a lot on these crystal analyzers. Basically, I did all the analyzer for the two beam lines, most of the analyzers. So the talk of today, I will try to keep as general as possible so everybody can understand. I will show a lot of pictures, no mathematical formula. I hope you enjoy this talk. So we start with a smaller description of the lab, followed by some detail on the main machine installed. Maybe you don't know about this machine. I will show the typical production of a laboratory, all the different kinds of analyzers we are producing, the reason of the production, why they are so demanded. At the end, I will talk about the research and development of the laboratory with the future development. So, the goal is a laboratory is completely dedicated to the fabrication of bent analyzer. It can be spherical or cylindrical for the moment. Is a sort of unique in the world because it's difficult to find all these machines grouped in only one place. Basically, I don't know any other facility has this possibility. This laboratory is operational since February 2015, and it was the first laboratory officially inaugurated on the ESRF in November 2015 with some of the SAC members. So before to go on, I want to go with the definition of bent analyzer crystal. Basically, the bent analyzer crystal is a thin wafer, can be germanium or silicon or other material bonded in a concave substrate. The substrate normally is glass, and you can find silicon, you can find aluminum, and so on. This is the most common of analyzer. We have a spherical analyzer here, spherically bent. Normally, the diameter is 100 millimeter. The curvature radius can go from 0.5 to 10, maybe even more, 11 meters. The other type, very known, is a cylindrical one. This is the dimension, maximum dimension I saw is 110 times 30 millimeters square. The curvature radius goes between 250 to 1000 millimeter curvature radius. This is the layout of the laboratory. The location is next to the ID 3V9. It took the place of the old surface science lab. It's quite big. We have available 120 meters square with a big clean room of 60 meters square. Basically, here you have the ring, you have the entrance. This piece here is only for the stocking area. Then we have a gray room. We call gray room because we have to enter with the surbot. And here we do all the manual operation, cleaning, using the anodic bonding press manually, and so on. We do some metrology. We have a chemical lab where we can do this chemical etching, also some lapping and polishing. But the real beauty is this piece here. It's this big clean room. It's a pseudo clean room, but it's very, very clean, so we have to go dressed very well on the SAS. And here we have all this beautiful machine. We have a dicing machine, a grinding machine. Here we have this anodic bonding machine developed inside the ESRF with a wood associated. We have another wood here with all the setup for the dice analyzer. We have a microinterferometer, we have a spin coater, and so on. This clean room is quite already busy, but nevertheless, we are going to install a second anodic bonding machine associated to this wood here, and another flue dot should stay here with all the material for the gluing of germanium analyzer. It's a spin coater, curing oven for the UV glue, and so on. Okay, so these are the people working in the lab. You have Christophe, the technician. He is a master of the bent analyzers. He is responsible for the production of the bent analyzers. I will go later to explain the difference between dice, bent dice, and analyzer. So he is also the master of the anodic bonding machine or the grinding machine. Concerning myself, I'm basically doing the production of dice, the bent dice analyzers, and I run the dicing machine and a 3-axis machine with a glue dispenser for the bent for a dice analyzer. And both we are taking care of the R&D development of the, with Ray Barrett that is responsible of the optics group. So here are some pictures. This is a clean room. We have this laminar wood with a setup for the dice analyzer. We have a microinterferometer here. This big laminar wood associated with an anodic bonding machine. So here there's another picture of an anodic machine with Christophe well dressed for the clean room. Here we have this two brand new machines called the disco grinding machine, and this is the IDT dicing machine, and this is for the wafer mounting, and this is a door for the SAS. We have also this small chemical lab, very useful. So 2 watts, one for acid and another for the solvents. We have a lapping machine to lapping the curved surface. And this is a great room for generic purposes. And we do all this gluing with the manual press here. Okay, so this is the first machine I want to talk about. It's called grinding machine. It's pretty huge. And we use this machine to reduce the thickness of the wafer and to do some polishing. Basically, 3 millimeters is the thickness of our standard wafer. It's the only thing we buy from the external company. 4 inches wafer with a thickness of 3 millimeters. And we reduce this wafer to an average value between 150 and 200 microns. The minimum thickness we can reach with this machine was 100 microns. It was a pretty nice wafer. So this machine is very easy to operate and very fast. So we can polish several wafers per day. We have 2 wheels here. It's polishing. One is for the lapping, and the other is for the polishing. You can see the teeth tested for polishing. This is the picture how you have the wafer out of the lapping machine. So this is basically you see all the sign of machining, and it's not very shiny. Okay, so the procedures, you take off as much as possible with a lapping wheel, and then the last 30 microns you take off with the polishing machine. At the end you have a pretty nice value. You have a peak to valley measured around 1.3 microns. You have an average roughness surface around 40 microns. It's the optical polishing. And we try also to measure some of this wafer on the BM5 with the topographic images. The wafer doesn't show particular stress after the machine. This is very, very good news. So, next machine is an IDT dicing machine. Here's the picture inside. We have this blade here, 2-inch diameter. It's rotating at 45,000 RPM. Normally are very, very thin. Normally you use 1 micron thickness. You can go also, I also have blades of 40 microns. Here you can see the chart where you put your wafer. Here's a camera to make the alignment. Here's what we call dressing table to clean up from time to time the blade. And here's the cooling water. Another value, nice value, is a blade exposure. The blade exposure is the distance here. It's the maximum dip. Is maximum dip of the cut you can go. So you cannot cut deeper than 4 mm with the actual setup. So this machine is used to dice wafer. Here we have an example. We can dice the very thin wafer. We can cut it completely through, or to make some casting with some index and leave some back wall. We can do also the circular casting, so we can reduce the diameter of our wafers. This for example, an example of 3 mm wafers, and this procedure takes 60 minutes to do the complete cutting. We can cut also this thick germanium wafers. This, for example, is 3 mm, cutted with an index of 1 mm on each side, to a dip of 2.8 mm. So you leave 0.2 mm of 200 micron backwards. This is the starting point for a dice analyzer that we'll show later. And then we have another application here, is what we call a pen dice analyzer. So we glue the analyzer, and then we cut through the glass as well. So just to reduce the stress on the wafer here. And this is very, very, very difficult. We cut through the silicon and pyrex, and this operation takes from 4 to 10 hours, depending on the index of your cutting. Okay, next one. This is a setup I'm using for my dice analyzers. Here is a 3-axis robot controlled by a laptop. Here you have a syringe with a glue with a very, very thin needles. Here you have the glue dispenser. And the goal of this equipment here is to put 1 drop of glue on each cube. So this procedure, we are sure you put the same quantity of glue on each tube, and you don't want the glue goes in between the groups. This procedure takes at least 2 hours. Okay, and this simple system is running since 1992. This all the dice analyzer we decided are done with the system here. So now, before to talk about the anodic bonding machine, I will introduce this anodic bonding technique. Maybe not all knows about this technique. This is a bonding technique very used in micro machining technology to build sensor. It's based on sodium-bearing glass. It can be pyrex, it can be Vorflow, and a semiconductor. Basically, silicon, or sometimes also germanium. So the principle, you take the 2 wafer, you have to clean very, very well the 2 surfaces, very, very flat, so no dust particle, no nothing in between. You contact the 2 surfaces, you apply a small pressure, and you raise the temperature. In our case, it's around 250, 350 degrees Celsius. At this temperature, you increase the mobility of the ions here. You apply the voltage. The value goes from between 1,000 to 200 volts. You have a current of few milliampere. So during this period here, the sodium ion, it goes to the they move to the to the anode, and for imaging, the silicon leaves some charges positive on the interface. So at the beginning you have an electrostatic bond. After a while you have a real fusion between the two wafers. This is a very, very strong strong bonding, and this very, very nice. It's a reversible process. There's no way you can separate the wafer again. You have this work very well if you match the two linear expansion coefficient. Otherwise, or you break everything, or the crystal is completely stressed. For example, for silicon, a good match is a Pyrex or this Borofloat R33. That is matched very well. If you put, for example, Pyrex in germanium, you will break everything. So this technique, I think we were the first one to use this technique on the spherical surface. So we did the first test with Menard already in 2001. So this is a very nice machine. This is called semi-automatic anodic bonding machine. This was an in-house project. It took basically 2 years of project. This is in the picture. It was a quite big investment for the ESRF. This machine is working very well and bonding silicon analyzer for a curvature radius with 1 meter and 2 meters. We call it semi-automatic because you need only to pre-clean the wafer and the Pyrex with this machine, the wafer machine here and the cleaner. Then you put it in the starting position, here the wafer and here the Pyrex concave. And the rest is, everything is automatic. So it's plasma cleaning, it's heating, voltage and pressure. So all this machine here is remotely controlled, and the process takes 6-7 hours. So after 6-7 hours, you can come back to the lab and pick up your analyzer. So that's why you cannot do more than analyzer per day. So to explain a little bit inside, this you have your wafer here your concave. These are 2 spinning stages, so they are spinning quite fast. This is the plasma cleaning and goes in and out. It can turn 180 degrees, so you can clean the upper part and the bottom part. When it's done, this is going inside. We have a valve for a vacuum. You make vacuum, and there is an automatic position in here that brings the wafer in the press here and the concave here, and then we have this press and do all the job. Okay, this is done for the automatic machine. Now I'm going to present all the kind of spherical analyzer in silicon we produce in the lab. The first one we call bent analyzer is a thin wafers, 150, maybe sometimes 500 microns bond on the spherical surface. Curvature ratio can be 1 and 2 millimeters, 1 or 2 meters. This is done with anodic bonding. You can find some other information on construction of this paper here. And this is used normally for medium energy resolution measurement. Okay, normally is around 1 eV, and depending on the curvature ratio, the curvature radius you're gonna use. The second type of analyzer we call bendized analyzer. Basically, the starting point is a bend analyzer, and we cut with our dicing machine through the glass some index. So in this case, we have the stress is limited to only 1 pixel. Normally, you have energy solution lower than 0.5 EV, and the beauty of this bendized analyzer that the energy resolution is uniformly distributed over all surface. So that means that if you put here 1 mask, or you leave the analyzer completely free, you have the same energy solution. This is not the case of this bent analyzer here, where you have the best energy solution in the middle, and the energy solution decreases as soon you open the mask. Then we have a bend new type of analyzer we call bend striped. This is has been developed for a very small curvature radius, in particular for 0.5 meters curvature radius. This is why, because if you try to bend even a very thin wafers on half a meter, most of the time you break the wafer. If you succeed on the bonding, the wafer is completely under stress. You have a very huge energy resolution, very stressed. It can be several electron volts. So in this case, we take the wafer, we cut it, and then we do the anodic bonding. So the energy resolution is pretty good, also at 0.5 meter. Here, in this case, here we have the stripes of 50 millimeter. But we do stripes here only for historical reason. The beauty of this technique, you can do whatever shape you can do. You can do squares, you can do triangles, whatever that your dicing machine allows you to cut. And this was a recent paper from Mauro Rovesi et al. Describing the technique and the result. The last analyzer, what we call diced analyzer, here are thousands of small pixel cube, normally with size of 1 by 1 millimeter, 3 millimeter of thickness, glued on a spherical surface. These are glued with epoxy. And the beauty here, that in this case, the crystalline planes are not bended, but are flat. So note this case here, the crystalline plane follow your surfaces. Here we have cube, glued, and well oriented on the spherical surface. This is used for milli-electron volt energy solution, and the curvature radius can go from 1, 2, and 6.5 meters. These are very difficult to build. It takes one day of 1 week of work to build this kind of analyzer. And here they're very fragile. Everything can go wrong in any moment. This is, we have to be very careful. To build this analyzer here is 1 day, and maybe from this one and this one 2 days to produce one analyzer. Okay. Then we start to build also this some cylindrical analyzer. These are pretty new for me. I build only a few examples, and I send all around the world to make measurement. Apparently they are quite good. I know only a couple of people interested in this one. Apparently the market here is pretty huge. These are also used very much in the industry. This is analytical bonding. This is normal. They are bended on a long dimension. The thickness is around 200 microns. And then we produce another type of analyzer, we call Johansson, and we explain later the difference between Johansson and normal cylindrical. Here I wrote bend, but here it is bend diced. So Johansson, because the crystalline plane they follow the curvature of your substrate, and the surface here is exactly half of the radius of your substrate. These are pretty much difficult to realize. Okay, so we go on. Where do we use this analyzer? We use analyzer for spectroscopic reason, basically in an inelastic scattering beamline. This is a layout of the typical inelastic scattering beamline, where you have a high heat load monochromator. Very often you have a high resolution monochromator here, a mirror, a focus on the sample. The radiation scattered by the sample are collected with these bent analyzers. They are refocused on the detector. Okay, to be on the better condition, you have to be with your sample, your analyzer, and your detector on this so-called Roland circle. The Roland circle, for example, here is a radius R/2, and the crystalline plane of your analyzer have to have a radius of R. Okay, this is called a Roland circle, and again, to reduce a small geometrical contribution, your error, you can have it to energy resolution. It's always better to be in the scatter geometry. So with the break angle very close to 90 degrees. If you are smart, you can put your sample and your detector on several of this Roland circle. You can build a multi-analyzer system. So this is a sort of collection of all the excitation spectra you can reach with inelastic scattering technique and with these analyzers. So if you have a very good energy resolution, you can measure phonon. Otherwise, in the minimum energy resolution, you can measure valence electron excitation, plasmons, core hole excitation, and also the quantum profile. Just to give you a sort of idea what you can do. So, as Claudia said at the beginning, in the last decade, we saw an explosion of this multi-analyzer spectrometer. We have a spectrometer building in all the parts of the world, and all this one are multi-analyzer crystal, and they continue asking for analyzer, all kind of type. At the ESRF, we have 6 beamlines that use this kind of analyzer. We have ID20, there's a Raman spectrometer with 72 band analyzer. We have also in the same beamline with a spectrometer called RIX with 5 band or diced analyzers. We have ID26 with 5 band analyzer, ID28, 9 diced analyzer. We have also FAME with 5 band analyzer. We have ID9 for the moment with only one. We have also Robler with for the moment with only one. But there are several spectrometers in construction. We have a very interesting spectrometer here on ID26 with 11 cylindrical Johnson analyzers. We have another couple of spectrometers in construction, BN23 and BN20. With, they can host a 5 band or band stripe analyzer with a curvature radius of 0.5 meters. We have also another pretty big spectrometer on a new frame with 4 band analyzers. And also we have another spectrometer in construction on 99 with 60 cylindrical band analyzer called bananas. So this explains the reason of this analyzer, the reason why the ESRF has been this enormous effort to put everything together and to build this crystal analyzer project. So now I want to talk a little bit, to describe a little bit some beamline in order to better show you how many analyzers are involved in this project. So starting from ID28, this is a beamline dedicated to the study of phonon dispersion in condensing matter at momentum transfer Q and energy transfer E, characteristic of the collective atom motion. This is an image of the spectrometer of ID28. They have 9 analyzers, diced analyzer, silicon 101. The curvature radius for the first row is 6.5 meters, for the second row is 9 meters. And with this analyzer, you can work with the energy resolution of the order 1 millielectron volt. So for the moment, we are happy with this analyzer. This analyzer was, I built it several years ago, and they are still there. For the moment, this not need to be upgraded. A second beamline has is ID26. Here, 26 high brilliance X-ray spectroscopy. They use several techniques: X-ray absorption spectroscopy, X-ray emission spectroscopy, and elastic scattering. Here they have spectrometers. This picture here you can find everywhere. They have a spectrometer. They can host 5 elastical band spherical analyzer. Here the curvature radius can go from 0.5 to 1 meter. Normally you can choose 0.5 or 1 meter. And here they need several reflections because they are going to measure absorption lines, emission lines. They have special energies. So every time they change the sample, they change also the set of analyzers. So they need many reflections. This ends up in maybe 100 or 200 spherical analyzer can be in silicon and germanium. Then we have ID20. ID20 is dedicated to the study of electronic and magnetic excitation in matter using resonant and non-resonant inelastic X-ray scattering and as well emission spectroscopy. In this beamline, they have the biggest spectrometers, it's called Raman here. On the Raman, you have 72 silicon 220 anodic bonding analyzers, it's shown here. We have 6 modules of 12 analyzers each. These 3 modules can move on the vertical plane and this one on the horizontal plane. And they work at fixed angle, very close to backscattering with a curvature radius of 1 meter. Here in the other picture, you can see the same modus with the characteristic vacuum chamber done in carbon fiber. Very, very light and very, very, very nice. So here they have 72 analyzers. They stay always the same. I'm sure that one day or the other, Marco Moretti will come to my office and tell me I want 72 bandized or diced or something else. So I'm ready to reach this new requirement. This is another spectrometer, very, very nice. I have on ID20s. It's called the RIC spectrometer. Here you can host 5 bandized or diced analyzers. They have this big chamber, and they can change the chamber with the possibility to use 1 meter or 2 meters. And they also here they are doing resonance inertial scattering, so they are choosing a very special energy resolution, and they need several reflections in silicon germanium. Here as well, you end up with another 150 analyzers. The beauty that the ID20, ID26, they can share the analyzer, so I don't have to do most of them. So here there are spectrometers in construction, just for some common interest. Here the spectrometer by D26, they call tender X-ray spectrometers. Here we have 11 cylindric Johansson analyzers in a row. Here I'm only showing 6, but normally you have 11. The curvature radius can go from 1 to 0, can be 1 or 0.5 meters, and they need 2 reflection, the 220 and 111. So this is ended up on 11 times 4 analyzers. I think I have to prepare the first series of 111 analyzers, 1 meter curvature radius for the summer 2017. We will do the first test. Another interesting spectrometers will be constructed in ID9 called Vanamos spectrometers. Here we have 16 cylindrical analyzers called Vanamos, and they are 4x4 with a curvature radius of 0.5 meters. And here you have 2 reflections needed for the moment. They have 111 and 5:1. And this will be ready for the end of the year. Okay. Now, this slide is only to show you that community is moving also all around the world. This is it's not a complete list of spectrometers for inertial scattering we have in the world. It's what spectrometer I know about. We have quite a lot of activity on SSRL with 2 very, very big spectrometers. A lot of activity also in Springate with these 2 green lines. These are diced analyzers on band. APS also is very, very active. There are quite a lot of spectrometers. Here in red are I presume it will be the grade. So they plan to have here more than 100 analyzers, here more 19. So these are a long tradition, APS, a long tradition on spherical analyzer, and they are building the analyzer themselves. So most of the U9 they build their own analyzer. We start to have quite a lot of analyzers also in Beta 3. They have a Raman spectrometer of 12 band analyzer. They are planning to build also another big spectrometer with 150 band analyzer. We have activity in Soleil, in Alba, and also IFER is coming. The European expert is coming to knock to our door with some requests for analyzers. So here, just give you a nice example of how many analyzers are involved. This is a database that our colleague did in APS. They call Analyzer Atlas. And this will give you all this near by scattering spherical analyzer you can use in RICS. They did all the calculation for silicon, germanium, lithium ion, sapphire, and quartz. So basically here you point an element and they give you all the available edges or emission lengths. For example, here I choose this case of iridium. They propose you this 3L line. So if you click here on L3, give you this list of analyzers you can choose. So I have several possibilities on silicon germanium. The better choice are the reflection they are processed at backscattering, so the first 2. Here they give you a certain value, but the thing that's interesting here, this is a intrinsic energy solution, and this they did some calculation for the geometrical contribution to the energy solution, taking in their case of 2 meter curvature radius and a source size of 50 microns. So they are expecting this energy solution here. And you have this one for all the elements on the showed in the periodic table. The funny things, you have a few choices for the cubic system, silicon germanium. You have 100 choices here for this hexagonal system. So you have sapphire, lithium white, quartz, and lithium white quartz. And this list goes on and goes on. 3 or 4 pages of reflection issues. And in principle, you can reach a very, very nice energy solution here as well. So if you do the calculation here, how many absorption line, every line has certain energy, certain set of analyzer, you have quite a lot of analyzer in a way. So this table here shows the production of the Crystal Analyser Lab. For example, I took as example the 2016 production to 2016 production. We did a total of 112 analyzers. We did 72 band, 5 bandized, 20 band stripe, 11 diced, and 4 bananas. Here is a distribution. We did 22 analyzers for the ESRF, 42 for the CRG, 28 for the external laboratory, and 20 are for sample keeping in the lab for sending acid testing in various analyzer facility, just to show the product all around the world. Here the production 2016. For the moment we have 24 analyzers, 16 for bent, 3 bent stripe, 5 bananas, 10 for the ESRF, and 14 for the external laboratory. So in total, since the beginning of the laboratory, we produce more than 210 analyzers. This is a list of various synchrotron and university and facility all over the world that ask the head of the laboratory to produce analyzer. We work quite a lot with Peter 3. We did some analyzer for BNL. We did quite a lot of analyzer for SLAC. We start to do quite a lot of analyzer also for XFEL, some analyzer for the Berlin University, Jena, Helsinki, Kwansei, Gakuin, Japan. Some analyzer for the Max Planck Institute, and now we start to do quite a lot of analyzer for Max Planck Institute, chemical physics of solids. So now, future developments. This is our R&D project. The most urgent here is for a germanium analyzer. These are highly demanded and very, very expensive. Expensive because the price of germanium is very, very high, and also because it's quite difficult to treat germanium. It's very, very easy to break it. It's very, very fragile. So the community is asking for bent stripe, and diced analyzer. So the problem I have here at this moment with the germanium analyzer is the body technique is not working properly. So some people think, oh, I didn't choose the right glass. So I don't find any help on the literature. So the idea is to start to use epoxy glue. That's why we already bought a spin coater, and we want to use a spin coater with epoxy glue or UV glue. And we did also a new manual press. So I hope to have some decent analyzer ready for winter 2017. Then we have other material, the quartz analyzer. Now the quartz is quite perfect. They grow the quartz in a very nice way. So these analyzers are more and more demanded. They are very, very expensive to buy quartz. The community asks Dyson analyzers. So with Dyson analyzer, you can work in a region between 10, 40 million volt energy solution. This are not commercially available, so you have to build it yourself. And it's particularly difficult to buy quartz. I found it's very, very difficult. Most of the producers in Japan, it's very difficult to communicate with them. Anyway, I have some samples, I have blades, I have everything. I hope to start the procedure and to have something measurable for the winter 2017 as well. Same story with lithium iodide. There are some requests up to now. These are expensive but not expensive at the quartz analyzer. The community asked for dice analyzer. The lithium iodide is not so perfect as a quartz, so you can expect to work in a region between 100 and 200 million volt. These are not commercially available as well. Here as well, I have samples, I have blades, and I hope to start the procedure and have something coming out for the spring 2018. I don't want to talk with the sapphire analyzer because this is a nightmare. Sapphire is very, very difficult to treat. It's very, very hard to cut, and it's even more difficult to make the etching because you have to warm up the etching solution. So this goes in very, very low priority. So here I want to show you the new anodic bonding machine that we are preparing. We call simplified because we don't have plasma cleaning inside. There is no automatic position, no motors, just a press and the temperature control. This will be helpful also for doing some tests to adapt the machine to the cylindrical, to the bend stripe, and so on. Now for the moment we are still missing the mechanic inside, but it will arrive next month, and we hope to have this everything ready for the summer 2017. This will allows us to double the production of pen analyzer crystals. We do that because probably we will have a very big order from Germany, so 150 pieces, and so with 2 analyzers for days, it's reasonable. So here I want to talk about Johansson ion geometry. So 90% or 99% of the bent analyzer crystal that are used now on the community are in so-called Johann geometry. In Johann geometry, you have your sample, your detector, and your analyzer on the Roland circle, and you have your Roland circle is a radius r, and the crystalline plane here are curvature radius 2r, and the surface here are also the same curvature of the crystalline plane. This makes some error of focusing on the detector position because you are you don't focus properly. To solve this problem, you have to go in so-called Johansson curvature. So here you have also this Roland circle, but you have a surface here. It has the same radius of your Roland circle. These analyzers are not so common because it's very, very difficult to produce. There are 2 ways to produce these analyzers. One is called single machining, and this is double machining. For the moment, I'm doing only this single machining. This consists in you can bond your wafer on the surface with curvature 2r, and you can machine the second surface with the radius r. This we can do it only for curvature radius not lower than 1 meter. 1 meter is okay. Half a meter I cannot do because I cannot bond here a very thick wafer. Another way to do this analyzer is so-called double machining. So you machine directly your wafer with a curvature 2r on the 2 surfaces, and then you bond this wafer on a spherical substrate with a curvature radius of r. So you end up with your plane, they have a curvature radius 2r, and your surface is r. This is called Johansson analyzers. So this cylinder Johansson are very, very expensive. You can buy it several companies, Saint-Gobain Crystal. You can do, we propose single machining and double machine. You can also have this startup industry here is starting to learn how to do it with single and double machining. We have some collaboration with Kaia. And then you have Rigaku. They propose a very, very, very nice crystal, but very, very expensive. So for the moment, we are start doing the production of single machining only. We plan to have a consistent, let's say, double machining cylindrical iones for the spring 2008. We are doing some work in this domain. So the first thing we want to try, we have a strong collaboration with the Crystal Lab. We plan to use this called XY polishing machine working very well in the lab. We want to implement a couple of plates. In particular, here you see the cylindrical plates, and we want to polish several analyzers at the same time. We want to polish in concave and in convex surface as well. So we have another plate here in brass to concave the both. For the moment, we have only half a meter here. This will be ready in a couple of months. In a couple of months, we have a way to polish this cylindrical one. Then last year, also in a Crystal Lab, we bought a very nice machine, new milling machine, very, very huge, very nice, very expensive. This is especially designed for abrasive material, like silicone, glass, porcelain. With this machine here, you can do all the shapes you want on your silicone. You can do curved surface, you can do holes, you can do a blow in the crystal. And last week, Benoit came in my office with the first prototype of double machining wafer. This is a wafer 84 × 20, 400 micrometers thick, with a double curvature. This is half a meter on the two surfaces. And this is a very, very nice starting point for cylindrical iones. So we are really on a good way. The goal is to go down to 200 microns here and to polish everything with a mechanical chemical way on this setup. This is all. I have only last slides for acknowledgement. Maybe I'm sure I forgot some people. As all the people more or less have worked in the lab, also on the beam line to test crystals analyzer, because without testing you don't improve your technique.
A big round of applause.
Thanks a lot for the
Who's asking the first question? Okay, let me ask the first question. How does the residual stress distribution look like in your spherical events analysis?
I don't know how you can measure it.
You can simulate.
You can simulate, okay.
That's the question where you know yourself best the answer, so this is a bit unfair. It goes more and more towards the end, because that's where the stress is highest. And then you see actually many experiments where basically the mass, the central part of the analyzer, and you have a mass of 20 millimeters, the resolution is getting very close to the theoretical one, and then if you increase the mass, you have a factor of almost 2
Factor 2.
between